Alright, hello everyone. It's good to be back. Today we're going to be looking at recursion part 2. Just as a quick review, we know that calling a function within itself is referred to as recursion. Recursion is at the heart of many algorithms such as dynamic programming and divide and conquer, and even whole programming languages. They replace the loop with recursion. It's also worth noting that anything that you can do with recursion can be done iteratively. And with that said, please keep in mind that recursion isn't always better than its iterative counterpart. So the first recursive algorithm I'd like to introduce to you is binary search. There's 3 main points I'd like to drive home for binary search. Number 1, it's an efficient searching algorithm. Number 2, the array or list that you're searching in, it must be sorted. And you're going to see why in a bit when we go through an example. And as innocent as it is, binary search is one of the most important algorithms we will talk about in this class. It's not only efficient, but it's clever and it's fast. It's also going to be used in many coding problems and interview questions you might encounter in your future. So when we say it's fast, we're going to need to compare it to something else. So without going into too much detail, we should really talk about how fast are algorithms in general. And so, without going into too much detail, like I said, algorithms in computer science can be classified by their speed using something called the big O notation. Now, the point of this slide is to kind of just introduce to you big O notation. We're not really going to delve into it too deeply. We're mainly interested in the algorithms here towards the bottom. We have order 1, which is our fastest. Then we have order log n, which is right near order 1. And then we have order n. So order n algorithms are anything that has to go through a list linearly, one by one. Order log n is anything that can cut a list in half every time it makes a move. And order 1 kind of means that it can access anywhere in a list at any time, it doesn't matter. So we just learned that for something to be logarithmic, it has to cut all the remaining elements in half every time it makes a move. So let's see how this works on an array or list. Let's say we're looking for the number 7. In an order n algorithm, we'd have to go through every element in the list and looking, is this 7, is this 7, is this 7? So using the second principle that the array/list must be sorted, we can take advantage that it's sorted. So the way binary search works is that we're going to access the element in the middle, and we're going to look at what it is. So we see here that the element in the middle is 5. Well, since the list is sorted, and we're looking for the number 7, we know that everything to the left, including 5, is not 7. So we can get rid of all those elements. They no longer matter. And we're just going to keep playing this game, where we look at the middle element. Is it greater or less than the number we're looking for? When you have an even amount of elements, you can choose arbitrarily if you're going to look at the left one or the right one. For this example, I just chose the left one and we do find 7. So an order n algorithm, which is linear, would look through every element in the list and it would take 7 steps to find 7. But in our binary search, we did 1 step, 2 steps, and we found the answer. So 2 to 7 for a computer is nothing. I mean, they're doing millions of calculations a second. But let's put this into perspective. If we had 8 moves on the processor for an order n algorithm, a log n algorithm would only take 3. The beauty of this is that the larger the number of elements get, it doesn't really affect log n because you're cutting it in half every time. So if we jump ahead to 1 billion elements, it would take an order n algorithm 1 billion moves to find if a number is in a list. So let's take a scenario that you're looking for the number 7 in a list. The list has 1 billion elements in it, but all the numbers are zeros. You don't really know that going in, you just have to look through the entire list. So you can't end early. You're going to go through every single element in this list looking for the number 7. However, if the list is already sorted and you use binary search, it would only take you 30 steps compared to 1 billion steps. And that's the power of binary search. So before we code it up, let's look at the pseudocode, which is the algorithm written out in text. So the way binary search is going to work is that we first compare the number we're searching for with the middle element of the list. If this is a match for what we're searching for, just return the index or return true, however you want to process that you found the right element. Otherwise, if the number we're looking for is greater than the mid element, then we know that our number can only be to the right of the rest of the elements. Therefore, we can get rid of everything to the left. So we apply the algorithm again to the right half. So the fact that we can apply the algorithm again on the same list lies itself to recursion. So I hope you can see how we're going to play recursion inside this algorithm. Likewise, if the number we're searching for is smaller than what's in the mid, we know that everything to the right is too big. We can just kind of cross it off, and we're going to apply the algorithm again to everything to the left. And just to kind of reiterate what I said in that text with a picture, is we're going to look at the middle element. If we're looking for anything that's larger than 5, we can cross off all these smaller numbers and then repeat our algorithm on the sub-array or sub-list, which would just be 6 through 9. Alright, so let's code up binary search. So as we know, we're going to have to search through a sorted list. So the first thing we're going to want to do is create a sorted list. And something I learned from my computer science 1 professor is how to create a random sorted list. It's pretty cool. Let me show you how it works. So we're going to use the random class, and we're going to create an empty list called sorted list. And we're going to want to first seed the sorted list with something. So we'll have sorted list dot append, and we're going to add a random integer between 1 and 50. So let's say we're going to have a list for I in range between 1 and 100,000. We're going to have 100,000 elements in this list. We're going to append the previous element in the list with a new random integer. Alright, so how this works is that, let's say we first seeded it with 34. It's going to take 34 and add another random integer between 0 and 50. It could be 34 again, that's still sorted. But let's say we add 10, now we have 44, and so on and so forth. So we're always going to have a sorted list with a set number of elements that we get to define here. Alright, so let's code up binary search. So as we know, we're going to have to search through a sorted list. So the first thing we're going to want to do is create a sorted list. And something I learned from my computer science 1 professor is how to create a random sorted list. It's pretty cool. Let me show you how it works. So we're going to use the random class, and we're going to create an empty list called sorted list. And we're going to want to first seed the sorted list with something. So we'll have sorted list dot append, and we're going to add a random integer between 1 and 50. So let's say we're going to have a list for I in range between 1 and 100,000. We're going to have 100,000 elements in this list. We're going to append the previous element in the list with a new random integer. Alright, So how this works is that, let's say we first seeded it with 34. It's going to take 34 and add another random integer between 0 and 50. It could be 34 again, that's still sorted. But let's say we add 10, now we have 44, and so on and so forth. So we're always going to have a sorted list with a random amount of elements that we get to define, with a set number of elements that we get to define here. And just for kicks, I think it would be cool to do a linear search through this list for the number 0. We know the number 0 will not be in here, so we're going to have to go through the entire list. And I want to just see how long it takes us, and then later on in the lesson we can compare and see how long did binary search takes us. So we're going to import another module called import time, and we're just going to say start time is equal to time.time, and we'll run our program. And actually this is a linear operation, so we could even time the adding of the elements, and that would make sense here. But we'll go ahead and write up the search function anyway. And we can have end time equals time.time. And then we can print something like all right, and then we can print it out and say something like the total time is the end time minus the start time. And we can see how that looks. Maybe we can say in seconds. All right, so we have the total time in seconds is 0.64 seconds, and we kind of want to get rid of all those extra numbers. Let's say our format is only going to go to 0.3, like 3 decimal places here. All right, so the time it took to insert 100,000 elements into this list was 0.66 seconds. And let's just kind of have fun with this. Let's say a million. .5 seconds. Let's do 10 million. And I'm still here. It's just taking so long to append all these elements to a list. And this is going to be why binary search is so powerful. I'll just cut to when it comes back. So that took 51 seconds. Wow. All right, let's go back to a reasonable number, 100,000. So one thing that I did, which might be kind of bad, is that I kind of just have all this code written out and it's not organized very well. So before I continue, I'd like to clean this up a little bit, and I'd like to create functions for everything. So create sorted list. And this will actually create a sorted list, append to it. We can keep the timer in there. That's fine. Print it out, and then at the end we're going to return the sorted list. And maybe we'll do the timer outside of the function. We'll just have this here for when we need it. I'm going to comment it out, clean up my function a little bit. So we create the function, we append, we insert all the elements, and we're going to get rid of all the time stuff. All right. So I'm going to say my sorted list is equal to create sorted list function. All right, that cleaned it up a little bit. All right, that cleaned it up a little bit. So now we have a function that creates the sorted list, and I can just call it and have a sorted list. And so I can actually have my timers here. All right, I can get rid of these lines. And let's see if it works the same way. All right, and this is a side note. Every time you run it, you're going to get a different number. Now, because we're not running it on our computer, we're running it through an online compiler. The operating system, so the operating system is always doing other tasks at the same time. So you're not always going to get the exact same time. And it also depends on the speed of your system. Like, my computer isn't going to be as fast as a supercomputer that's on a server. So this might be faster than the time it takes on my computer. My desktop is probably faster than the time it takes on my laptop. It's interesting to see how fast different computers will process the same information. Another thing to note is that, let's say my laptop provides a faster number than my desktop. That's not concrete enough evidence to say that my laptop is faster than my desktop. And the reason is that the operating system, which is processing your code, is also running other processes. And so if it deems some sort of Windows update to be more important to process at that moment than your code speed will suffer. And this is the reason why Big O actually came to be, is that you can't just time code and be accurate of how fast it is. Now, you can get a good guesstimation through timing code, but it's not the end-all be-all. But it's cool to see, it's fun to play around with, and I encourage you to just kind of play around with all the code that you're seeing today. So to just get a recap of what we've done so far is we've created a sorted list, and we've timed how long it takes to perform that order and operation of creating the sorted list. This will give us a reference to compare our binary search algorithm to kind of show how much faster it really is. Now, I understand that this is a recursion lecture, but recursion's kind of the backbone to the algorithm. All right, so let's go ahead and write our binary search recursive algorithm. So we're going to want to create a function called binary search, and we're going to want to take in a few parameters. We're going to have the list. We're going to have, I'll call it my list. We're going to have the element we're searching for, which is our key. We're going to have a starting index, and we're going to have an ending index. And the reason we have a starting index and an ending index is when we call the function again from within itself, we're not going to be changing the list. We're simply just going to be saying, hey, this is your list. This is its new start element, and this is its new ending element. So we're kind of lying to the function. We're saying, oh yeah, there's a list, here it is, but these are the only elements you're allowed to access. With all recursion, we need a base case. And so our base case here is going to be whenever the starting index is greater than the ending index. If we ever cross those pointer lines, we've hit an end. So if start is greater than end, we're going to return false. And you can return the index or you can return false. It really depends on however you want to process this finding or not finding. All right, so now we're going to have to find out where the middle element is located. And the best formula for that is to take the start plus the end minus the start divided by 2. And the reason we don't do something like this, mid is equal to start plus end divided by 2, is that if start and end are both very large numbers, you're going to overflow and then your mid is not going to be accurate. With this formula, it doesn't matter how big start or end are, you're never going to overflow and cause an error with which index you're actually looking for. All right, and then we're going to look. If the key is equal to the list mid, then we found it. We're going to return true. And then we have two other options. If the key is less than my list mid, and then we have if key is greater than my list mid. And this is where the recursion is going to happen. So if the key is less than whatever element is in mid, we know that everything to the right we no longer need. And if the key is greater than what's in mid, we know that everything to the left in the list are elements that are too small to be our key. So at this stage, we're going to return the function itself. We're going to pass the same list. We're going to pass the same key, but we're going to pass the same start because the key is still less than whatever's there. We want to start at the same location, but our new endpoint is the middle element minus 1, and we minus 1 because the middle element wasn't the element, so we're just going to get rid of that one as well. If the key is greater than whatever's at the middle element, we're going to return the opposite. We're going to return binary search. It's the same list. It's the same key. Now our start point's going to be different. It's going to be the mid that we calculated plus 1 because the middle element wasn't what we were looking for, so it must be smaller. And then the ending element is going to be the same. All right. So let's go ahead and call binary search on the sorted list. The key is going to be 0, and I'm choosing 0 because I know 0 can't be in this list. We started creating the sorted list with a random element of 1 to 50. So if I choose 0, I know that we're never going to find it, and whatever time we get for binary search is the absolute worst case, which is how we want to compare with the order n algorithm. So then our start index is 0, and then our ending index is the length of my sorted list. So I'm just going to run that, see if we get any errors, see if I made any mistakes. Okay. So here, my mid calculation due to the way I divided it, it thought it was a floating point. So I'm just going to take this entire number and convert it to an int. All right, so it compiles now. Let's go ahead and time it. Let's see. Let's create a new start time, a new end time, and the total time. And I'm also going to print out the result just to show you. It should say false. I should have done that at the first place, but let's see what happens here. All right, false. And it took 0 seconds. If I get rid of the formatting here, let's see how long it really took. It's so small that it doesn't even show up at 3 decimal places. So we're going to do that same experiment where we do 1,000,000 elements. And I don't like that it's doing, I want to put the 0.3 decimal places back in here and run this again. Still 0 seconds. So I'm going to do 10 million and I will cut to when it comes back. Again, it doesn't even show up. It doesn't even register. So I know this is a recursion lecture and it kind of turned into a sorting, searching, and efficiency lecture, but it's cool to see how a recursive algorithm can just find its way into something so magnificent such as binary search. And how simple is this algorithm? We said in the beginning that binary search is very simple, but don't underestimate it, because you can use binary search to solve a lot of problems very quickly due to how fast it can process an entire list. Alright, so the next problem we're going to look at is a strictly recursive problem. It's a problem that seems like it would be difficult to solve, and then you see the recursive solution and you're kind of like, wait, how does that work? But it works. This will be a fun recursive problem to look at. So you probably have seen the Towers of Hanoi at some point or another. Once you see a picture of it, you'll know what I'm talking about. But you have 3 towers. Let me just skip ahead. You've got 3 towers. Only one disk can be moved at a time, and only the topmost disk of any tower is the one that can be available for moving. Also, a wider disk can never be atop a narrower disk. So if I moved the blue one over to the middle, I couldn't put the purple one on top of the middle. I have to put the purple one on the goal. So this is just a fun problem where it has a very nice recursive solution. So let's go ahead and do a couple just on paper. We're going to move the blue ring over to the middle, or the auxiliary array. We're going to move purple over to the goal. We're going to move blue over to purple, and then we're going to move green to the middle. We can move blue over to the start. We can move purple over to the middle, blue on purple, and then red to gold. And I kind of just, these took a while to make, so I kind of jumped to the end, but you get the idea of how it works. The rest of the process would have been the same process, just kind of in a different order. So if we were to solve this problem iteratively, it would be a mess. And this is kind of where recursion is an awesome tool to have in your programming toolbox. The general idea for the recursive solution is that you can move the first 3, or if you're talking about it in general, so if you have n rings, you can move n minus 1 rings, which is the first 3, over to the middle tower using the goal tower as an auxiliary pole. And we kind of proved that here, where you can flip between middle, goal, and start and have and have all the rings line up on middle, and you're just left with your last ring, which is your biggest. Then you can move this biggest ring over to goal and kind of perform the same back and forth using start as an auxiliary pole. So if we were in that step before, we could use start as an auxiliary pole to hold n-1 rings, and you're left with your last ring. You can put it over to your goal. Now you're using start middle as the auxiliary, and you're left with one ring which you can put over to the destination. So the idea is that we can move n discs, as many discs as we have, from the start tower to the end tower using a single intermediate tower. So it might be you might not trust it right away, but for recursion you got to trust it and then put the solution in, and then somehow it works. It's pretty interesting. Alright, so I apologize, I know that was rough. I don't think this is going to be any simpler. It's almost a confusing definition, but you got to trust it and it works. So let's create a function called towers of Hanoi, and it's going to take in a ring amount. It's going to have a source pole, a destination pole, and an auxiliary pole. And as with all recursive functions, we're going to have a base case. The base case is if the ring amount is 1, we can just move it from whatever source we're at over to the destination. And let me make this a little bit bigger here. All right, and then we return from that base case. Otherwise, we're going to move n-1 rings over to the auxiliary pole. So we're going to call our function with n-1. Our source is the same, but our destination is the auxiliary array. And our auxiliary is the destination. I might have spelt that wrong. I'm just going to copy these. So to just make quick sense of that, our goal here is to get to this step using the goal pole as our auxiliary and our middle pole as our destination. We're trying to move n-1 rings over to the middle pole using the goal pole as an auxiliary. And once we are at this stage, we can move the final ring over. It's our base case. So we can print at this stage that we move the disk, and whatever disk we're on, from source to destination. And so once we're at this stage, we're going to want to move n-1 rings from the middle pole over to the start pole using the goal as an intermediate, so we can move the last ring, the green ring, over to the goal as a destination. So once we've moved our n-1 disks over to our auxiliary array, we can move our final disk over to the destination. Then we can repeat this process using the auxiliary array as the source and the source as the auxiliary array. So we can kind of call our function again with n-1 elements, and our source this time is the auxiliary array, Our destination stays the same, and our auxiliary array is our source. And that's it. Those are all the cases that we'll run into. So you can kind of see how sometimes recursive solutions are much simpler than their iterative counterparts. We don't even want to begin to code up the iterative towers of Hanoi. But at the same time, this is also really hard to understand. It kind of doesn't even make sense that it works, but it does. And let's actually run it and make sure it works before we say that. So we're going to say towers of Hanoi. We have 4 rings. That's what our example was. Our source is A. Our destination is C. And our auxiliary is B. Well, let's go ahead and run this. All right, and I'm going to pull up the PowerPoint as well to kind of go along with it. All right, so move disk 1 from A, which is our start, to B. Move disk 2 from A to C. Move disk 1 from B to C. Move disk 3 from A to B. Move disk 1 from C to A. Move disk 2 from C to B. Move disk 1 from A to B. And then move disk 4 from A to C. So that's the exact process that we had come up with. And if we continue here, move disk 1 from B to C, which would be blue over to red. Move disk 2 from B to A, so we'd have purple over here. Move disk 1 from C to A, so then we'd have blue, purple, and then green on its own, and we'd bring green over. We'd bring blue to middle. We'd bring purple over and then blue over. And it looks like our algorithm works. So this is just a fun program to show you how powerful recursive solutions can be. Alright, that will conclude Recursion Part 2. I hope you learned something, and thank you for spending a little bit of your time today with me.